Okay, everyone, welcome back. Hope you had a good break. Hopefully, you all got a chance to demo Lab 2 a week before break. Lab 3 is posted, and that'll be due on April 4th. And I'll talk more about that in Lab this week. Quiz 5 is also posted, and you have till I think it's Sunday, actually, March 20th. Yeah, Sunday, not Monday, sorry. As usual, you have till Monday night to take, or sorry, Sunday night rather, to take the quiz. And this quiz will be the second quiz on SystemVerilog. Okay, so we also had exam 1 the week before spring break. The grade distribution there was pretty flat, so I couldn't do a curve on the exam, but I'm sure we'll have a curve on the final grade for the class, the semester scores. The average was 77.5 and the median was 75%. I don't want to go over every exam question today. If you have any questions about an exam question, let me know. I just wanted to call out the 3 questions that had the lowest scores. So the first of those was question 3 that said, which line of code will insert the value 7 into the variable val into a bit field spanning bit positions 9 down to 7. Obviously, this is a bit manipulation question, and I was surprised that this one had such a low overall score. So the idea here is that there's 4 choices. The first 2 are taking val and doing a bitwise OR with itself, and the second 2 are taking val and doing a bitwise AND with itself. OR is when if you want to insert bits into a field, you're going to want to do an OR. So the answer has to be one of these 2, and then the question is, how much do we shift the value that we want to insert by? And the options are 7 or 9, and 7 or 9 are the 2 sort of the both ends of the field. And so in this case, we want to shift it by 7, which is the lower end of the bit field, because the value 7 is 111. This is a 3-bit value, and we're shifting its starting bit to bit position 7. But it will, because it's a 3-bit value, it will end up spanning the 3 bits from 9 down to 7. Okay? So the answer there is 1, or A. The second question was, assume an SPI channel has CFI equals 0 and CPOL equals 0. What happens first during an exchange? Now this question, I can understand that this one was hard, because this was a little vague. The options are MOSI transitions to its first value. So it's basically asking what happens first. What's the first signal to change in the SPI channel, in other words. Now, as you remember, the clock only operates during the transaction, or during the exchanges, I should say, right? Only when the bus is being used to communicate. So it isn't necessarily going to be the clock that's going to be the first thing to change. So in this case, you would have to look at, well, you wouldn't have to, but I think an easy approach here would be to look at those timing diagrams that I had on the slides. And so if CPOL is 0, and actually, I think CPOL being 0 is redundant here. It actually doesn't have any effect on this question at all. CPOL rather, the polarity, clock polarity, doesn't have any bearing on this. The CFA describes when the data changes relative to the clock. And CFA 0 means the data has to start changing before the clock changes. And so that's the first thing that happens here, is that the data changes. Now you could say, well, wait a minute, what about SS? I mean, SS drops at the same time the data changes, which is true, but that's not one of the options here. So the answer we're looking for is MOSI transitions to its first value. MISO does too. MISO also does, but MOSI, that's the best answer. You guys see that? So in other words, that happens, that's the thing that happens in here, farthest to the left in the timing diagram. And then question 18, and I understand why this one scored low too, because this one was a little, the units here were a little deceptive. I said, suppose a UART channel has a baud rate of 19,200. Now, in that case, I don't give units because baud rate is always expressed in terms of bits per second and uses 8 data bits, 1 parity bit, and 1 stop bit. What's its maximum throughput in bytes per second? So I kind of threw you a curveball here because normally I think in the quizzes I ask for bits per second, but in this case it's bytes per second. So you have to do the calculation and divide by 8. So the idea was that you take 19,200 and multiply it by the ratio between the payload, which is 8 bits, over the total number of bits that are transacted, which is data start stop parity, which is 11. So 8 over 11 is the ratio. And that ends up being 13,964 bits per second. And then you have to divide that by 8 to get 1,745 bytes per second. Notice here I've got lowercase b is bits and uppercase b bytes, a typical convention. So it's 1745. I think this is the lowest scoring question, and I think I assume it was just because of the I think a lot of you might have missed the units there. And also, the second option actually matches the bits per second calculation. So I kind of tricked you there. It wasn't my intent. I was just trying to come up with a novel way to ask the question, because I think I asked the same question on the quiz with bits per second. Okay, so that was the exam. Those are the four toughest questions on the, or sorry, 3 toughest questions on the exam. Then we also had quiz 4? Yeah, quiz 4. And that was the first quiz on SystemVerilog. What's the problem with the SystemVerilog module below? In this case, you've got 2 assigns. Now remember, an assign statement is a circuit, is a digital circuit, and so this would be 2 circuits driving Z. This is potentially causing a conflict, right? This is because it's implied that this is push-pull logic, which is similar to how SPI works, as opposed to open drain, a design of I²C. So signal Z is potentially in conflict is the answer. Does SystemVerilog support structural or behavioral? Both. Consider the following SystemVerilog modules. We've got 2 modules here. Top is the top level, bottom is the bottom. And so we've got bottom instanced here. We call it my thing. And what is the value of A and Y within my thing? Okay, so this gets confusing because of the renaming. So we have A and Y in bottom, or actually, in my thing, because that's what bottom is called when we instance it here. And we have A and Y inside top. The problem is that when we instance my thing, we connect its Y, sorry, it's A, my thing's A. So we connect the port A to the signal Y inside top. You guys all, you see that? Does that make sense? Now I don't know why you would do this, because this is, this makes it hard to read. And then the Y port is connected to A. So we're basically just swapping Y and A. So inside of my thing, A is going to be a 1, right? Because we're sending in Y, which is 1 here, right? So A is going to be a 1. So it's got to be one of these 2 answers. And then Y is connected to A, but A is not assigned anything, right? So it would be X or Z? Z, right? It would be Z. Which one's right? Oh, 1 and 0. Okay, that might be, I might actually screw that up. Y is 1, and A is not assigned. Oh, sorry. Actually, I take that back. So yeah, so the idea is that inside bottom, I forgot that one of these is an input and one of them is an output. That's what's going on. So my thing, the A is an input and the Y is an output. So that's why I only assign the input, obviously, because if I were to assign the output in here, then it would be, if I assign something here inside of top, it would be double driven, right? Because remember, my thing, because it has an output Y, it's a driver of signal A. You guys see that? So I can't set A in here, because if I set A in here, like with an assign, for instance, then I would be assigning it with an assign statement and also assigning it with my thing. You guys make sense? Okay, so anyway, yeah, so inside my thing, Y, which is actually bottom, right, within my thing, which is my thing is a bottom module, A is going to be 1 and Y will be 0 because we invert that up here, right? So 1 and 0, yeah, that's right. Okay, how many bits are in the following constant number? It's 11. It says 11 apostrophe, it means there's 11 bits. Now, there's only 4 bits specified, and so because there's 11 bits here and I only give 4, then the rest of them are zeros, right? It's going to fill in the rest with zeros. The left, so we've got basically 4 bits given, right? And then there'll be another 7 zeros, but those 7 zeros will be to the left of these 4 bits, right? So we kind of fill in the left part with zeros. Okay, how many bits comprise the signal A? This is a little misleading. I mean, this is the thing, one of the things I don't like about Verilog, right? You would think it would be 3, right? But it's not, because it's 3 down to 0. So it's 3, 2, 1, 0. It's actually 4 bits. So you always have to add, you know, when you see this, you have to add 1 to that value in the left spot. I don't know what, I hate that. I hate that syntax. It's needlessly confusing, but that's just how Verilog works. So it's going to be 4 bits. To what value is A set in the SystemVerilog snippet below? Okay, so so this one is a ternary statement. So in the operator precedence, the ternary statement is evaluated at the very bottom of the precedence list, right? So the ternary, so you might say, like, why don't you have parentheses here? You don't need them, because the ternary is the lowest priority. So everything in the conditional part of the ternary will be evaluated first. So it's going to compare this, and then it's going to evaluate the ternary to 1 if it's true or 0 if it's false. Now this is redundant, by the way, because if I had just put in the condition by itself, which is this, if I had just put this in, then it would already evaluate to 1 or 0, because that's how conditionals in Verilog evaluate to a single bit, 1 or 0, right? Having this ternary operator where I check the condition and evaluate it as 1 if it's true and 0 otherwise is just redundant. But it's still valid, right? Okay, so we're going to take, now if you look up the operator precedence, the shift will happen before the double equals, which we can confirm that here if we look at the table. If I have a table, yeah, there it is. Yeah, so shift is above double equals, right? So the shift will happen first. It would have been easier to read with parentheses, but it's not technically needed here. Oh well, I should say it would be more readable with parentheses. Right. So there's a value, 2-bit value that's decimal 2, which is going to be 1, 0. I'm going to shift that to the left by 1. So that's like multiplying it by 2, right? So that should be 4, 1, 0, 0. And then I want to check to see if that equals 4, encoded in 3 bits, 1, 0, 0. And of course that's true. And so that will be evaluated to 1. Okay, in the SystemVerilog snippet below, to what value is signal A set? So we've got A is declared as a 4-bit logic value, and we assign it to, we assign it in reverse using these curly braces to the octal the 4-bit octal value 10. Okay, so that would be 4-bit octal 10 would be, that's the value 8, right? And 8 is in binary is 1000, right? So it's going to reverse that. It should be 0001, right? This guy. You guys see that? Makes sense? Okay. All right. Consider the Verilog module shown below. How many input signals are specified? Now, I don't think I covered always yet, right? I don't think I got to that in the last lecture, but it doesn't matter because the question is just asking about the module line. So how many input signals are there? There's 1, 2, 3, 4, right? 4 inputs and 1 output. So 4. Now this could be a little confusing because of the way it's written. Because the input keyword comes before clock reset load, right? Because all 3 of those are 1-bit inputs. And then I have another input keyword in order to change the width of the next input seed, right? So there's 3 inputs, and then there's the 4th one, even though the word input only shows up twice. Okay, any questions? Okay. So today I'm going to try to finish up the SystemVerilog lecture. You have a question?
When will the labs be graded? I've checked my Dropbox and I was wondering when the labs would be graded.
That's a question for Phil. I thought we had Lab 1 graded.
Lab 1 should be graded. The grades are not posted. Most of the class did extremely well on Lab 1, so I will have the grades up on Dropbox probably this evening for Lab 1. For Lab 2, give me about a week.
Okay.
Yep. Do we have everyone demo Lab 2?
Most of the folks have demoed Lab 2.
I think I got a couple emails from students who couldn't make it to lab last week, so they got an extension to demo this week.
Okay. But I picked up 1 or 2 demos today, so.
Okay. Okay.
Yeah, I think we're about done collecting demos.
Okay, so hopefully very soon.
Okay, I'm just making sure.
Yeah, thank you. Okay, so last lecture we talked about hardware description language, which is a high-level language used to describe the structure and the behavior of hardware. There's 2 things you can do with SystemVerilog code. You can't really compile it like you can a normal high-level language. You can simulate it in a simulator, or you can synthesize it into hardware, which converts the code to hardware that you can then either deploy either on an ASIC, custom integrated circuit that would have to be fabricated, or an FPGA, which is a programmable logic device, right? It acts like a blank slate. In this class, and I'm not sure how well, this is a little experimental, but my goal is to have us only do synthesis in this class and skip simulation, because I covered simulation in 611. In this class, I want to focus on synthesis more because we don't do as much of that in 611. Right? I'm trying to come up with a complement. This is supposed to be complementary to 611. Now, the downside of that is that in order to test your designs, you're going to have to synthesize them onto the FPGA and then put probes on the FPGA to watch what the signals are doing, right? The problem with that is that it increases the iteration time, right? So in other words, you make a change to your code, you want to see what the impact of that change is, but now I got to synthesize, right? And then I have to deploy it on the FPGA and run it to see what's going on. So that could be a little problematic, except the designs you're doing in this class are going to be very small, so hopefully that won't be too much of an issue. Okay, so 611 we do almost entirely just do simulation. In this class I want to do entirely synthesis. Okay, that's my plan. I haven't tried this before though. So I was thinking about this over the weekend. SystemVerilog is actually a very simple language syntactically. There's not really much you have to know about it as compared to like C++ or Java, right, where you've got a lot more complex things. In SystemVerilog, there's really just 5 things you really need to know. You need to know how to create a module, so that module line that has the inputs and outputs, right, and it goes in its own file. It's not required that it's in its own file, but that's the convention most people use. You have to be able to declare I/O signals for the module as well as internal signals inside the module. So you guys comfortable with that idea? So the I/O signals are the signals that come in and go out of the module, whereas the internal ones are just inside, interior signals. And by the way, the I/Os, local signals inside a module are generally used to connect other modules together that you instance inside of there. They kind of act as glue, right? Number 3, instance and connect other modules inside of modules. That's structure. So that's basically creating like a block diagram or a schematic using Verilog. And we've looked at that already. Number 4, the assign statement, which is the way that you create simple combinational behavior, like a mux, for instance. And then number 5, which we'll talk about today, is the always statement that's used for memory and clocked behavior. Logic that uses the clock signal. That's it. You know those 5 things, and you know SystemVerilog, or at least enough to use it. So it's in 4 of those we've already covered in one lecture. So like I said, it's pretty simple. It's really not that complex of a language, at least in terms of designing SystemVerilog that you're intending to synthesize. Now there's a lot of things you can do in SystemVerilog in the language that is not synthesizable. But if your plan is to take a module and put it into hardware, these are only 5 things you can do. Okay, now there's a few odd things that I don't like that make it hard for you to learn SystemVerilog if you're coming from Python or Java. The first thing is that the order of the assigns and structural statements, in other words, the instanced modules, don't matter. You can scramble them in any order. It doesn't matter because you're building hardware, and SystemVerilog uses concurrent semantics, meaning that the order of statements doesn't matter. Now, there's some weird caveats to that, one of which is if you declare a signal, you have to declare a signal before you use it. You still have, obviously you have to do that in Java, but you have to also do it in Verilog, which makes no sense because declaring a signal is like saying, well, the wire exists, it's called A, so why would it matter where you instance that wire? But for some weird reason, the compilers enforce this. They want you to declare signals before you use them, even though the language inherently is concurrent. So that to me is dumb, but they require that. It's probably because of the parser, when they designed the parser. They have begin and end statements that begin a basic block. So if you have a multi-line if statement or a multi-line always statement, you have to put begin and end. It's equivalent to curly braces in Java. Why begin and end and not curly braces? I don't know. That's bad. You have to actually type begin and you have to type end. It's horrible. Don't know why they do that, but you have to get used to that. Semicolons, you have to put a semicolon after the module line. Why? You don't put it after class line in Java or C++. Why after the module line? Unclear. But you have to get used to that. And then the array bounds, as I mentioned when I was going over the quiz, array bounds basically are 1 less than they should be. So if you want a 5-bit signal, you have to say 4 down to 0, 4:0. Why? That also applies, by the way, to RAM, which is a 2-dimensional array. It applies to both dimensions. Dumb. Don't know why they do that. Okay, so you got to get used to those 4 weird things, and then these are just the 5 things that you got to know. So we talked about the design hierarchy where you have modules instantiated inside of other modules, and we also talked about this idea of regularity where you try to design modules that can be used often, like repeatedly, like an array, right? And this is the way that chips become 10 billion transistors. It's not because someone actually wired up 10 billion transistors, because that's impossible. The reason why chips have so many transistors is because when they're designed with this hierarchy, and they're designed with regularity, where 90% of it is copied and pasted structures that repeat over and over again, right? So that's the reason why you can have such high levels of integration, and that's really what this is all about. That's what SystemVerilog is doing for you, is giving you the ability to very easily create these design hierarchies. The problem is that the design hierarchy is fake. It's all made up, because when it's put into hardware, the hierarchy is flattened into a big mass of wires and transistors, right? So this whole design hierarchy is only there in your design. Once you deploy it in hardware, it disappears. So what ends up happening is that if you have a signal with one name in this module that's connected to another signal in this module with another name, it's the same signal, it's the same wire, two different names. But when you look at the design on the FPGA, which we're going to do in this class because we're going to put probes in the FPGA to test things, you don't know which name to look for, because all the names get deleted except for one. Yes?
So, I apologize. I feel like this is a stupid question, but there's something that's been troubling me. I don't really understand the link between the C files that we're writing and the Verilog files that we're writing that get compiled down into an actual circuit.
No, that's a good question. That's a great question. So, if this were a pure hardware design course, like 611, you wouldn't be writing any C files at all. It's just all Verilog, right? The problem is that at some point people realize that computers are complex enough in their behavior that you can't implement things in Verilog practically. All you can do in Verilog is create very simple reusable structures to create a CPU, which then executes software, which is very easy to program. So the presumption here is that anyone can program in C. Anyone can program, that's easy, anyone. But designing hardware is really hard, right, comparatively, right? So the idea is that we want to minimize the amount of hardware design we have to do, but we want to maximize the things that the hardware can do, right? So we design like in the case of this class, we have a Neos processor which is implemented in Verilog, although you can't see the Verilog because they encrypt it. They have to keep it secret, even though it's a very simple architecture. But the Neos processor is Verilog, and then we're writing C that runs on top of that, right? Make sense?
Yeah.
Now you might then say, well, wait a second. If you've got a processor that can do pretty much run any Turing complete program, in other words, anything a computer can solve, the Neos can solve it. Why do we need to design any more hardware? Like why don't we just say game over? You know, we're done with hardware design. The reason is because software is also very slow compared to hardware, and most importantly, it's non-deterministic. You will never know how fast that C code runs. It's impossible, because there's cache misses, there's interrupts, there's all kinds of non-deterministic things that happen. So you'll never be able to, for example, you'll never be able to truly have a real-time system in software, because you'll never really know what the worst-case execution time is, because it's impossible to account for all of these cache misses and page table misses, page faults and interrupts and all the things that go on with the CPU. So when it comes to real-time systems, oftentimes you'll have hardware design, like specialized hardware, right? And what this class is all about is cyber-physical systems that are controlling the physical world, and those always have to be real-time, right? So that's kind of the idea. So we're doing hardware-software co-design. So in this next lab, just to kind of give you a preview, we're going to be writing C and Verilog that are going to work together. The Verilog is going to give us a way to do the pulse width modulation stuff that you did in the last lab rather ad hocly, because most people don't do PWM in software, it's done in hardware. So we're finally now going to do that in hardware. And then we'll write some C code that communicates with that module. Does that answer your question? Yeah, so the C code is running on an embedded microprocessor. The Verilog code is creating hardware that, generally speaking, the hardware does very low-level things. If you want to do complex behaviors, you move that into software, unless unless you want to improve its performance, in which case you have to put it in hardware. Does that make sense? Okay, yeah. So that's a really good question. This class this is a purely like a hardware software co-design. We're designing both at the same time. Okay. So I talked about that. Okay, last time we talked about modules. So we've got the module line with the, semicolon at the end of that. Module line gives a name for the module, has the inputs and outputs. And then there's an end module without a semicolon, and everything in between those two lines is the implementation. So we can put, like, for example, an assign statement in there, or we could instantiate something else in there. So if you put an assign, that's called behavioral. If you put other module in there, that's structural, or you can put them both. You can mix and match. Like I said, behavioral is logic gates. Structural is building hierarchy out, essentially. And like I said, this is a case where you've got both. Okay, now when you simulate, or even if you test designs on an FPGA, as we're going to do, you're going to be looking at that as a logic analyzer, as a plot, where the horizontal axis is time, and you're looking at signals going high, low. This is meant to look like an oscilloscope or like a logic analyzer. It's a plot over time. You have to get used to reading these, and as you would imagine, that's the reason why we started this course out with SPI and I²C, because of course that was all about reading timing diagrams. But whenever you do hardware design, it's all timing diagrams, because that's really the only way to conceptualize the behavior of the logic, is through a time. Some people use a list, which basically creates like a spreadsheet where every row is whenever a signal changes. That's kind of like what we gave you in Lab 1, actually, when you looked at those trace files. So you could look at a trace file, but usually in software you see it as this timing diagram. Okay, so I mentioned the ternary operator, which is right out of C++ and Java, but it's used in Verilog to create a MUX, conditional assignment. So we can assign, this Y can be assigned to D1 or D0 based on S, which is a MUX. Right? So this should synthesize directly to a MUX. Internal signals are declared internally, and they're used to glue together either modules, or in this case they're gluing together assignment statements. So we've got A and B come in, they kind of pass through this P and G stage, and then they get passed into this second assign stage, which then ultimately sets S and C out, which are the outputs. Okay, so a couple notes about SystemVerilog syntax. I think I got through this last time. It's case sensitive, which shouldn't surprise you because every language you've used so far is case sensitive, but VHDL, which is the other popular HDL, is not. So just be aware of that if you end up ever looking at VHDL code. Identifiers can't start with numbers. White space is ignored. Comments are the same as in Java. And as I mentioned, basic blocks use begin and end instead of parentheses. Here's another example of a full module. So we have module AAA, inputs AB, output C, and it basically just calculates a straight up Boolean logic, not A and B assigns that to C. Notice the not is a tilde. It's kind of weird, because in Java it's a bang, it's an exclamation point. In fact, you still have exclamation point in Verilog too, but tilde is the bitwise negation in Java, right? So I'm not even sure when it would matter whether you use tilde or explanation. I generally use tilde for negation in Verilog. But yeah, not A and B. Notice that's a single ampersand, which is the bitwise version. I believe, Verilog also has the double ampersand, but when we're doing bitwise calculations, use single ampersand. And this just creates a truth table like the ones that you guys use in 211. So this is a very simple module. You probably, by the way, would never create a module like this. You wouldn't create a whole module just for one line of code. Generally, if you need this behavior, you would just paste that into another module you need it in. You might say, well, how do you decide then how to create a module versus just inlining code? Well, it's usually it's for regularity. If you need this behavior a lot, then it would be good to have it in a module, except it's just one line of code. Usually you try to have, usually modules are like, several lines of code. But it's entirely up to you, though. That's all stylistic stuff. Okay, and then we talked about numbers. So whenever you have a constant number in Verilog, you should explicitly give the number of bits, followed by a parenthesis, followed by a base, which can be D for decimal, O for octal, B for binary, H for hex, followed by the number, right? You can also put underscores in there to separate fields of bits out. The underscores are ignored, but they're just used for readability. So in this case, it's 8 bits, binary value 1010 1011, which turns out is actually the decimal value 171. Octal characters are 3 bits. So 4 is 100, and then 2 is 010. Right? So 100, 010. So the first 3 bits were the octal digit 4. The second 3 was the octal digit 2. Together, they're 6 bits. And so we have a 6 here, although this could be 8 bits, in which case it would be adding, 2 leading zeros. Yes?
Just making sure the behavior for it doesn't have enough bits to store the bit-wise representation of the number is that it truncates everything but the least significant bits?
I think it would give you an error if you did that. Like if you said 2 bits and then you put the value 8 in there, I think it would I would expect it to give you an error. If it doesn't, then it would, I'm not sure what it would do. It might truncate. I haven't tried that. It's a good question. But the compiler would know, because it's a constant, so it would know that there's not enough bits. Okay, so this is where we I think ended up last time, the always statement. So this is the last major piece that you need to know about SystemVerilog. The always statement is it's technically a statement in the sense that it's like one statement, one semicolon at the end, but you can embed a begin and end block in here, a basic block inside here, right? So in which case it's multiple, it can include multiple statements embedded in a block. The idea is that you give a sensitivity list, which is the list of signals which, when they change, that's when the always statement is evaluated. What it really means is that, that's one way to think about it, but what it really means in terms of the deployed hardware is any of the signals in the sensitivity list will potentially cause the output to change. So now you might say, well, okay, but you're just talking about the inputs, right? You got logic. If the inputs change, the output may change, right? If the inputs change, the output may change, right? That's only true for combinational logic. Combinational logic being, logic with no memory. If you have sequential logic that has internal memory, like a flip-flop or a RAM, then the idea is that the sensitivity list is the clock, basically. Right, so when the outputs only change when you get a clock edge. That make sense? Mm-hmm. So generally speaking, these always are used for clocked logic. You can also use them for combinational logic, but then it's like, well, why not use an always statement then? I'm sorry, then why not use an assign statement then? Sorry. So there's 2 different behavioral things that we're learning here. One is the assign statement, which cannot be clocked. It's only for combinational logic, lookup tables, or truth tables, basically, Boolean logic, right? That's the assign statement. The always statement is mainly used for clocked logic, sequential logic, right? But you can also use an always statement to make combinational logic, in which case it's just a complex form of the assign statement. You guys with me? I know that's confusing, and it's another one of those things that I don't like about SystemVerilog, and I say that because I've been teaching it for a long time, and I know that it's one of those things that is confusing. It's hard to teach because it makes no sense. I mean, why do we have a statement here that can make, clocked or unclocked logic and another one that can only do unclocked. It's just weird. I don't know why they did it that way. But that's the idea. So normally I try to stay away. I don't generally use an always statement to do combinational logic. I only use assigns for that. The only exception is if I have a really complicated if-then-else block that I want to do, which is in 611 we use it for the control unit of the CPU. So the control unit's this huge if-then-else table. If the opcode is 0 and the function code is 1, then it's an add instruction, right? If the opcode is 0 and the function code is 2, then it's an AND instruction. But if the opcode is 6, then I don't care what the function code is, but then you have to look at the RT field, and if it's 0, 1, 0, then it's a branch of equal. That's the kind of thing you have to do in the control unit, right? And so that we generally do that in a big if-then-else block inside an always, right? Okay? Okay, so in an always statement, you can put if statements, which you can't do outside of an always statement. You can do case statements, and you can do regular loops, although I've never actually used a regular loop. There's also a generate loop, which we will use in this class, but a regular loop that actually, creates an actual loop. I've never put one of those in an always. I've never found a need to do that. Okay, so this last bullet just kind of summarizes what I've already talked about. The only thing you can put in an always, the only thing you can put in a module outside of an always statement is assign statements, structure, and then always statements. You guys with me? I know it's hard to remember that, but the bottom line is you can't really put much in a module in terms of behavior unless you wrap it in an always statement. That's kind of the idea. Okay, so let's look at some examples here. So if we say always at ABC, y equals A or B or C, then that's just equivalent to saying assign y equals A or B or C, right? Of course, if I put both of these in here, it'll create a conflict because both of these, the always and the assign, are two pieces of logic. They're going to conflict with one another. They're going to double drive y. So I can't put them both in. I can put one or the other, in which case they both do the same thing. So when would I use one or the other? Well, like I said, my style is I would use the assign because it's easier to read. Right, and that way I can use the always just for clock logic. Okay. Also, if you have an always statement that drives an output y, and I put a module that drives output y, that's also a conflict. So I can have a conflict between an always statement and assign, or an always statement and another module. Does that make sense? Now you might say, wait, hold on. Well, how do you know that y is an output from the always statement? You don't, other than the fact that it shows up on the left hand of an assignment statement inside the always block. Does that make sense? So the always assigns y internally, is part of its always. This module also assigns y, which we know just because one of its ports is called out, and it's pretty obvious that that's an output port. We don't know it's an output port from this line. You'd have to drill down and look at the module description to know that for sure. But I'm assuming that this guy's driving y, and this always statement is driving y, so this would be a conflict. You don't want to do that. Okay? Does that make sense? I'm not sure if I'm explaining this as well as I could be. But the point is that an always statement is a blob of logic, is a circuit. An assign is also a circuit. And if I create a submodule here, that's also a circuit, right? So this is basically, what I'm showing here are 4 lines of code. Each one of these lines of code creates a circuit. Right? This is a structural line of code because I instantiate another module, but these first 3 are behavioral because always and assign are our behavioral idioms. Okay? Behavioral meaning it actually does something other than just creates a schematic. Right? Remember that a lot of Verilog code is just schematics. All this structural stuff is just, this, I want to create this and connect it to that. I want to create this and connect it to that. That's just schematics, right? The behavior is when you actually have it do something, like create logic, Boolean logic of some kind. Okay. All right. So here is the most common usage of an always statement is to create a flip-flop or a register. Okay, so you guys, I'm not sure how much you talked about. Did you guys cover flip-flops in 211? So a flip-flop is basically a holding, like a storage slot, right? So it captures a bit and holds it there until the next clock cycle, right? It's basically what it is. It creates memory. It's used for creating pipeline registers, which hopefully you covered in 212, as well as finite state machines, which you probably didn't look at those yet. But it's just clocked. It's just memory. It's just a type of memory that you can build in a circuit using cross-coupled wires, essentially. You have gates that where the one output feeds into the input of another one, and then that one feeds in the input of the first one. So you have this cross-coupling of wires. This creates it creates memory. Okay, so what I'm showing here is five always statements. The first one says always underscore FF at pause edge clock, Q gets D. This is literally just a D flip-flop, right? So on the positive edge, this is edge sensitive. On the rising edge of the clock, Q is going to get the value, is going to take a snapshot of D, and that snapshot is going to move out to the output, and it's going to keep there until the next snapshot, which is going to be on the next positive edge of the clock, next rising edge of the clock. Make sense? Now you might say, wait a second, why is there a less than sign there? That wasn't on the previous example, right? We had a equal sign there. There's an equal sign here, and there's a less than equal sign here. It looks like an arrow. Why is that? That is the syntax you use for memory circuits. Sequential logic use this assignment. For combinational logic that doesn't have a clock, you use this assignment. Another thing that's kind of obnoxious about SystemVerilog. I forgot to put that on my list, on that list I had in the beginning of the lecture. But that's obnoxious. Easy to forget too. You guys with me? Now there's actually a more detailed explanation behind that, which I'll get to in a minute. But just for now, this is because we used an equal sign here because there was no clock. No clock mentioned here, right? But because there's a clock mentioned here, we use less than equal. That's the only difference. Okay? Okay. Any questions about that? Does that make sense? So this is how we would build, like for example, if we were building an SPI channel in hardware, we'd have to have clocked logic, right? Because there's a clock in there, right? Same thing with I2C or UART. Anything that kind of changes its behavior over time needs a clocked circuit, sequential logic. Okay, now there's some variations you can do here. Now, by the way, you might say, wait a second, sensitivity list, pause edge clock, why is D not in there? Why is D not in the sensitivity list? It's explicitly excluded from the sensitivity list because if the whole point of this is that if D changes, nothing happens. D gets ignored until there's a clock edge, and then we snapshot it. We capture it, right? Does that make sense? So the whole point of this sensitivity list is to not have D in there. The fact that we don't have D in there and we have the clock in there is what makes this a flip-flop as opposed to a truth table. Okay? Okay, so then we can create a D flip-flop, and we can add a reset. Sometimes you have a reset, like you want to, like you just connect a reset to the reset button on your computer. You hit the reset and it clears everything, right? So you can just add an if statement. If reset, then clear the queue, otherwise capture D, put in queue. Make sense? Now notice that reset is not on the sensitivity list either. And that has an implication that the reset is synchronous, meaning that the reset by itself doesn't do anything. It's ignored unless you have reset high and then a rising edge of the clock, in which case it'll reset, right? Now, on the other hand, you can add a reset to the sensitivity list, as in this case. This will create an asynchronous reset that will allow you to reset it independent of the clock. Because this way you say pause edge clock, pause edge reset. There's a comma there. I think you could also say and pause edge clock and pause edge reset, but I like this syntax better, the comma. This just same logic. The difference is that this guy, if you put reset high, it resets immediately. It doesn't wait for the clock. And the only thing I have to do to make that happen is put that reset in the sensitivity list, right? In this case, pause edge reset. Actually, if you just put reset and not the pause edge, that would be the same behavior, because that would activate on a falling edge of reset, but then, but see, no, it wouldn't have the same behavior. So check it out. If you didn't put the pause edge reset in here, right, then this always would activate on the rising edge of clock or on the falling or rising edge of reset, right? Now what would happen is that if reset went from high to low, it would activate the always, right? And then the if statement would not follow this if reset, because reset is 0, right? So, but it would clock D into Q, right? So if I didn't have the pause edge reset, the reset falling would be would be treated like a clock edge here, right? Now we don't want that. Okay, does that make sense? Okay. Okay. DFF, D flip-flop with synchronous reset. We already did that. Oh, this has an enable. Sorry, this has an enable too. Sorry, this should say synchronous reset and enable. Sorry, yeah. Okay. So there's an enable here. So this one adds an enable signal. So it puts a enable condition, so it has to be enabled. So you have to have a clock and it has to be enabled. This would be used for something like a what did you guys have in 212 that had an enable? Well, like the register file, right? You don't always write a register. You only have to enable it. It's like a write enable, right? Okay. So in other words, if you don't have an enable, then the D flip-flop's output will change every cycle. Every single cycle you'll update Q with D. But sometimes you don't want to do that. Sometimes you want to take a value of D and hold it across multiple cycles, in which case you need an enable. Okay, and then lastly, you can actually embed logic, like arithmetic and logic, inside these types of things. So in this case, you could create a counter. In fact, this is exactly what we're going to do for lab 3. Lab 3. We're going to do a pulse width modulator in Verilog, and so fundamentally we're going to need a counter for that, right, to keep track of the duty cycle, right? So this is a counter, always FF pause edge clock. Every clock edge you increment an internal count, Q. So there's no D here, right? There's no input D. Notice that these guys have a D. You might say, well, there's no input. You don't specify input anywhere. Well, no, but we don't even reference D here, right? D is not even on the right-hand side of the assignment. So D is ignored because it's just a counter that will continuously count. It'll add 1 to Q every cycle. Every clock edge you increment Q by 1. Does that make sense? So that's just a counter that counts as fast as your clock. In fact, this is the same thing the performance counter did in the last lab. You guys remember that we had a performance counter that basically just counted once per clock? That's all it was just this. We had this, and then we could read the value of Q with the NEOS. We couldn't read it every cycle because that's too fast. CPU's too slow to do that. But it was always being updated every cycle in that module. Okay? Does it make sense? You might say, well, why can't you read it every cycle? Well, because in order to read it, the NEOS would have to issue a load instruction, right, to load it across the bus, right, in programmed I/O, and then generally there'd be a couple other instructions there before it could load it again, right? So you can't read it every cycle because you can't issue a load I/O instruction every cycle. It's too many other instructions that have to be put in there. Yes?
So this page, are these pseudocode? Like these aren't?
No, these are actual code. This is actual Verilog.
Okay.
As far as I know, these all compile and work.
Okay. Why don't you need to specify, for example, what D is?
You do. It's a snippet. So the idea was D would have to be declared outside of these snippets. These are not full modules. And that's a great point. So before I was showing you, like here, I was showing you a whole module, right? Now you might say, well, wait a second, you didn't declare C. Yeah, I did. It was declared to the module line because it was an output, right? It's not an internal value. C is an output here, right? So it's kind of like an argument on a method in Java, right? So I can assign it, even though I didn't declare it internally because it's an output. But this is a whole module, right? So this is a self-contained module. What I'm showing in that other slide was, these are snippets. These would go in, these are little snippets of behavior that you would put in a module, right? And yes, you're right, you would have had to declare Q and D would have to be declared somewhere. That is correct, as well as clock and reset and enable. They would have had to be, they do have to be declared. I should have made that more clear. That's a really good question. Okay, here's an example of a whole module now that does have an always flip-flop in it. Now, one other question you might have is, wait a minute, what's going on with the always underscore FF as opposed to just always? These are always underscore FF, these are always. What's the difference? I don't know, I think I might have mentioned this last time. If I did, it was right at the end of the lecture. The underscore FF doesn't do anything other than it provides a layer of checking for the compiler. So if you have always FF, the compiler then will make sure that this will create a flip-flop. It'll make sure that you wrote it as a flip-flop. Right? If you didn't write it as a flip-flop based on the way that your sensitivity list and internal structure is, then it would give you an error. It's just a way to check you. If you just use always, then there's no checking. You may end up writing, you may intend to write combinational logic, and you may get a latch, or you may get a flip-flop, right? And that's a mistake, but it wouldn't be caught by the compiler because you never told the compiler. See, this is, by the way, symptomatic of the problem I mentioned earlier, which is, why have one always that can do combinational logic or sequential logic? Right? Why do you have this one statement that can do everything, and then you've got another one, the assign statement, that can only do combinational? That's dumb. Yeah, it is, and it creates problems because it's a way for bugs to be introduced. If you have a bug in your code, you may have a bug in your code because of that. Well, in SystemVerilog, they introduced this underscore FF and underscore com, which is an attempt to fix that problem, which is a way to tell the compiler, hey, I'm trying to create clock logic here, so if I didn't do it right, then flag it as an error. Right? If you don't put the FF, you don't have to, but then the compiler doesn't have a way to check you. Does it make sense? I know it's a subtlety, but the reason I'm pointing it out is because in the next lab, we're going to be creating a module in Platform Designer. You know how you guys have been using modules in there? And this is, by the way, I'm excited about this because in 6.11, we just create straight, as I mentioned, there's no C programming, right? It's just straight Verilog. And then in 3.13, if any of you guys are in that or have taken that, we just use Platform Designer, and it's only C programming, no Verilog. Now we get to do both. I'm going to try to have you create a module that we can, in Verilog, that we can instance in Platform Designer. And that way you can write C code that talks to your hardware, like you can write software that talks to your hardware, right? That's the objective of the next lab. The problem is that when you do that, Platform Designer forces you to use Verilog and not SystemVerilog. And so that underscore FF won't work because for whatever reason, when you do a module for Platform Designer, they don't let you use these SystemVerilog features. So that's why I'm pointing this out. Okay, and I'll talk more about that a little later. Okay, now let's switch back now to structural Verilog. I've already talked about this, but we're going to come back to it just so I could show you some examples. And I like this. I'm pretty proud of this series of slides because basically what I'm trying to show here is how the Verilog is translated to a block diagram, a schematic. This is doing schematic capture with Verilog. You guys with me? What's a schematic? It's a picture. It's a design, a picture of a design. This is a text design, right? So in Verilog, you have to write text, but what you really want to do is draw a picture, right? And there are actually tools where you can draw a picture and it will generate the text. I used to teach one in 611, but we dropped it because it was more trouble than it was worth. And also I found out that in industry they don't use that stuff. They just write straight Verilog. So I felt that I was crippling the students in our program, because if they go out and work for a company like Texas Instruments or NVIDIA or Intel that actually make hardware, they're not using the picture stuff. They're just writing in straight Verilog. But the concept is you still have to sort of imagine it as a schematic though. Okay, so what am I talking about? Okay, so I've got this thing called NAND3. So NAND3, when you write the module line, you're creating a symbol for NAND3, which is a box currently empty, but I have A, B, and C are inputs and Y is the output, right? So that's all I've specified in this red text is this, right? Then I create an internal wire called logic N1. N1 is my wire, and that's like creating a wire in there. I just take a wire and drop it in there, right? Internal wire, right? And then I'm going to create a 3-input AND gate, which I call AND gate, but no one cares because that name is only for the purposes of this design and for simulation. So it's an AND3 and an inverter, and I'm going to plop those in there. Now, in order for that to work, I also have to have those defined in their own module files, right? Which they are up here. So AND3, I put that in. Inverter, I put that in. And each of those now have port maps, A, B, and C, and Y on the AND gate, and A and Y on the inverter. They might say, why'd you call it Y? I don't know, actually. I got that convention from the textbook. It could have been called alt or Z. It's Y. Y is the output on these guys, right? Notice I have a Y in the NAND3 here, global Y is the output, but then these submodules have their own Y outputs, right? Okay, and then, so that's what these do, but I haven't connected anything yet until I get to the connection, until I highlight the connection part in red, which is what then creates the connections. So I'm going to connect A to A, B to B, and C to C, which means I'm going to connect A on the port to A on the top level input, B to B, C to C. So that creates these connections. Likewise, Y is going to be connected to not the top level Y, but N1. So Y is connected to N1. Y on the 3-input AND gate. Does that make sense? Okay, so now I have, these inputs are not renamed, it's just A, B, and C. But the output on the AND gate is called Y inside the AND gate, but it's going to be called N1 inside the NAND gate, right? The NAND gate is my top level design here, right? So now I have Y in there is equivalent to N1 in here, right? So now when I flatten this, by the way, when I synthesize this on the FPGA, one of these two guys is going away. Like the FPGA software will drop one of these because they'll be like, well, I don't need, it's the same wire, right? So I'll call this signal will either be called, it might be called AND gate dot Y because it was the Y in the AND gate, or it'll be called, NAND3 dot N1. It's not going only one will survive, right? But for the purpose of this design, you got one wire that's called N1 inside this scope, and it's called Y inside that scope, right? Okay, so then I'll connect N1 to the A input on the inverter, and the Y output on the inverter will be connected to the top level Y using this code. You guys see that? I don't know if you can read it in the back, but A on the inverter, the A input, I'm going to connect it to N1, and the Y output I'm going to connect to the, my Y. His Y, my Y, connected together, right? So now I end up with, if I look at this as a glass box, I've got, the NAND gate with the AND gate and the inverter inside and connected, right? Now this is why I call these internal signals just kind of like glue, right? N1 is the glue that glues together the AND gate and the inverter. Make sense? So if this makes sense, then you understand how structural HDL works. Because VHDL is the same way, works the same way. VHDL is very similar in the sense of creating structures. Okay. Okay. Now, if I were to simulate this, or if I were to probe it on the FPGA with JTAG probes, logic analyzer probes, of course, I would probably have zeros, the counting sequence on A, B, and C, and then look at the corresponding Y. So I'd make sure that Y is what I expect it to be. In this case, Y is always 1, unless A, B, and C are all 1, in which case Y is a 0, because it's a NAND gate. That's how NAND gates work. Okay, any questions about that? Okay. All right, so here's an example question. I think I already asked one like this on the previous quiz, but how many total bits? Well, not really. I actually phrased this a little differently. On the quiz, I asked how many inputs and outputs are there, right? There's 3 inputs, outputs, 2 inputs, 1 output, right? A, B, and C. But this question says how many total bits comprise the inputs? And it just says inputs, right? So how many bits are the inputs? Well, there's 2 inputs, and they're 1 bit each because I don't have brackets here. There's no brackets that define these as multi-bit. So these are basically just 2 bits, right? There's just 2 bits, A and B, 1 bit each. Oh, I don't have the end. Okay. Here's another example. In the SystemVerilog code below, to what value is signal A set? Oh, it's another one of these reversal things. Okay, so this is right from the quiz, pretty much. So I got this thing called my thing. It's of type bottom. Module type is bottom. I've got an A and Y here. I've got an A and Y in bottom. But the problem is when I create the port map, I swap them. So now in this case, I'm not asking about bottom. I'm talking about top. So what value is A set to? It's going to be set to the output of bottom. And the output of the bottom is the inverse of the input. And the input was A. In this case, it's called Y. So Y goes in, gets inverted, comes out as 0, right? So A would be 0. Does that make sense? That confuses me. But the problem is that you've got A and Y in both designs, but they are reverse connected as I go from top to bottom, right? So what's happening is that Y is A in bottom, so just think of Y as the input, A as the output, and the thing is inverting. So because I'm assigning Y, I'm assigning 1 is the input, 0 will be the output. In this case, 0, the output is A inside of bottom. Does it make sense? Okay. Here's another example, similar, except in this case, I assign A. But now I've got a problem because I assign A here and I assign A here because this guy, because Y is an output and I connected it to A, this counts as driving A. But this assign statement also counts as driving A. It's its own circuit. So now I've got a conflict. Now the question is, how is this going to manifest? Well, it's going to be bad. It's going to be the worst case scenario because my thing is going to be trying to set A to 0. We know it is because the input is 1, so the output is 0. So this is going to be trying to set A to 0, and this assign is trying to set it to 1. So now not only do I have a double-driven signal, but it's actually double-driven in the bad way, where you got a disagreement there, right? So this will end up becoming X in the simulator, right? And if you did this in actual hardware, it would result in a potentially damaging the chip. Unless it gets caught in the compiler somewhere and doesn't let you compile and deploy it. Okay. All right. So here's the operator precedence table. I think I've already talked about this. One of the interesting things about Verilog is that you've got multiply, divide, and modulo operators in Verilog. Right? The problem is that there's no way you're going to synthesize these. I mean, you wouldn't want to. These three operators are enormously complex, especially divide, to implement in hardware. In fact, a lot of chips don't even have divide instructions. I don't think the Neos does. You might say, wait a second, I can write a divide in my C code and compile it for the Neos. Yes, but it doesn't get mapped to an instruction. It gets mapped to a function. It calls a function and does a divide in software using shift and subtract instructions. I don't think the Neos has a divide. I could be wrong about that, but I don't believe it has one. The ARM v7 architecture, which is the one that's just previous to the one that everyone's got now, didn't have a divide. Divide is really, so they might say, wait a second, if divide is so hard to make in hardware, why do we have a divide symbol here? And presumably if we use this in a module and synthesize it to hardware, it'll create a divider circuit, right? Yeah, it will, and I've tried this once. It turned out that I put that in one time. For 611, I put it in some Verilog, and I synthesized it, and it ate up the whole FPGA, just that one operation. And I don't even know if it worked. I mean, I don't know if what ended up happening was it exceeded the capacity of FPGA because I was trying to use it in a processor with other hardware. So generally speaking, you won't use these in synthesized code. You'll actually have a module that does a divide, usually in multiple cycles. Okay, and then bit manipulations. I think I might have talked about this last time. But basically, it's pretty much what you would expect if you looked at the code. What these bit manipulations do is allow you to take curly braces, and you can use these to concatenate signals, smaller signals into a larger signal, or smaller values into a larger value. And when I say smaller, I mean in terms of bits. Okay. Also, you can slice out. Like if you have a signal A and I want to extract field 2 bit 2 down to 1, you can extract a field using the brackets, right? And again, you probably would expect that would be what that does. Okay. Okay. So here's an example of that. This is a sign extension circuit. So this takes a 16-bit value of B, and it creates a 32-bit value of B, and it does it through sign extending. So the idea is that if bit 15 on B, which is the sign bit, as a 16-bit value, it's going to replicate that. It's going to drag the sign bit out and use it to fill in the other 16 bits, right? Which is the way that you would do a 16 to 32-bit conversion if it's a signed number, right? Because you wouldn't want to inadvertently change the sign. Okay. Now you might look at that and say, well, that's awful. That's awful to have to write that. Yeah, there's a simplified way to do that too. This syntax, which is whenever you have two parentheses nested like this in Verilog, so left parenthesis, or sorry, not parenthesis, brace, or curly brace. Left curly brace, right curly brace, right curly brace. This format is taking the value inside the innermost curly braces and reproducing it by 16 in this case. Right? Now this syntax is a little non-intuitive, I think. I don't like this. I think this is fine. This makes sense, but having to copy and paste that is silly. So they introduced this replication operator. It takes bit 15 and copies it 16 times, and then concatenates it with B. You guys with me? Does that make sense? Did you guys learn about sign extension in 212? It's just basically it's you think of it like a binary type conversion, right? 16-bit type to a 32-bit type. And so you replicate the sign bit because if it's a sign number, you want to keep the sign bit. Okay, I think I'm out of time, so we'll see you in lab on Wednesday and Thursday.